Exponential functions. Objectives: identify the base of an exponential function and restrictions for its value. Find the equation of an exponential function. Evaluate exponential functions with base e. Given two data points, write an exponential function. Identify initial conditions for an exponential function. Find an exponential function given a graph, and sketch a graph of an exponential function. Our basic exponential function. If b is greater than 0 and b is not equal to 1, then the exponential function with base b is f of x equals b to the x. Exponential functions in graph format. Sketch a graph of y equals f of x. Identify the y-intercept, domain, and range, and give the equation of the asymptote. Here I have f of x equals 3 to the x. If I let x equal negative 3 from my t-table, I'll have 3 to the negative 3. 3 to the negative 3 is 1 over 3 cubed, which is 1/27. 1/27 is our output. If x is negative 2, we would have 3 to the negative 2, which is 1 over 3 squared, which is 1/9. Output of 1/9. If I let x equal negative 1, 3 to the negative 1 is 1 over 3 to the positive 1, or 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9, and 3 cubed is 27. Now, placing these points on my coordinate plane, I have at negative 3 a very small number of 1/27. At negative 2, a little bit larger number of 1/9, still quite small. At negative 1, 1/3. At 0, 1. 1, 3, 2, 9, and by the time I get to an x value of 3, I've shot up to 27. Connect our graphed points here, and you can see a good idea of what this graph looks like. Now, if I would pick x's less than negative 3, that number would get smaller and smaller, but never quite get to 0. Okay. In fact, you can see that if we are going this direction in the function, every number is 3 times the number before it. If we're going the other direction, then every number is divided by 3 to get the number before it. The y-intercept here is 0, 1. The domain, we can see, is going to be negative infinity to positive infinity. The x is in an exponent position, and it can be anything that it wants to be. The range, we can see, is a result of the outputs. I look at my outputs. To the right, I'm going to be going up to positive infinity. To the left, I'm getting very close to 0, but we can see there's never going to be a negative enough exponent. Even if I had an exponent of negative 100, it just makes it a very small fraction. So as I move to the left, my y value is getting closer and closer to 0. So my range is from 0 to positive infinity, not including the 0. And my asymptote is this horizontal line of y equals 0. Now let's try graphing y equals 1/3 to the x. It might be helpful to start from the bottom of the table for this one. 1/3 cubed is going to be 1/27. 1/3 squared is 1/9. 1/3 to the 1 is 1/3. 1/3 to the 0 is 1. 1/3 to the negative 1, if I had 1/3 to the negative 1, that's the same as 3/1 to the positive 1, which is 3. If I have x as negative 2, then I have a 1/3 to the negative 2, which is 3/1 to a positive 2, which is 9. If I have an x of negative 3, then this would be 3 to the positive 3, which is 27. Familiar values from the graph that we had before. So at negative 3, I'm all the way up at 27. Negative 2, I'm at 9. Negative 1, I'm at 3. 0, 1, 1, 1/3, 2, 1/9, 3, 1/27. So we're getting this kind of graph as we go to the right, and as we go to the left, going up to infinity. My y-intercept is still 0, 1. The domain, again, x is in the exponent, and it can be any number, negative infinity to infinity. The range, by looking at our graph, we see is 0 to positive infinity, not including 0. And again, the asymptote is y equals 0. In fact, g of x is a reflection of the graph f of x here over the y-axis. Another way to write this function would be 3 to the negative x. In this form, we can see more easily that this is a reflection across the y-axis from the knowledge that we have about transformations to this point in the course. Here we can see the characteristics of the graph of f of x equals b to the x. I have a family of graphs sitting here, y equals 2 to the x, and y equals 1/2 to the x. We can see as one is increasing, the other one is decreasing. Let's look at the characteristics listed. It says here that the points negative 1, 1 over b, 0, 1, and 1b are on the graph. In regards to the red graph, our base is 2, so this would say that the points negative 1, 1/2 is on the graph, and I can see that here. 0, 1, of course, these are all going through the point 0, 1, and 1, 2 are on the graph. There we go. And this is consistent for all of the graphs that are listed here. Now, if b is greater than 1, if my base is greater than 1, this is going to be an increasing function. That is going to be all of these graphs here, all increasing functions. If my base is between 0 and 1, then the graph is going to be a decreasing function. The x-axis is a horizontal asymptote, we can see, and the domain, negative infinity to infinity, and the range is going to be 0 to positive infinity, not including the 0. Now let's see if we can look at a graph from a function that's already been placed on the coordinate plane, and let's see if we can find an equation for that exponential function. This one is of the form f of x equals b to the x. When I look at this, I can see it's going through the point 0, 1, as was listed in some of the characteristics of exponential functions. Now, I'm looking at 1, 2. At 1, for an x, I have a y of 2. This makes me think that my base is probably going to be equal to 2. Let's see if we can find this. Y equals 2 to the x. And let's see if this fits the pattern for what we want in our graph. Okay. If x is 0, y is 2 to the 0, which is 1. If x is 1, y is 2 to the 1, which is 2. There's my point, 1, 2. If x is 2, y is 2 squared, which is 4, and we would see the point 2, 4 on the graph. And it looks like so far so good. Let's try just one more. If x were negative 1, y would be 2 to the negative 1, or a positive 1/2. A negative 1 and a positive 1/2 is exactly where we want that to be. Now there's a more analytical way that you can try and figure out what the function is here, and I'd like to show you that. I know that I start out with this function y equals b to the x because we've been told it's of this form. Let's pretend we don't know what the base is and we need to figure this out. Well, I do know that I have this point 1, 2. Perhaps I can put that in for x and y, substituting them, and then find the base. This means that my y is 2 from that point equals b to the x, which is 1. Well, I know that b to the 1 is b, and b is 2. So, in an analytical way, we have found f of x equals 2 to the x. Exponential growth. A function that models exponential growth grows by a rate proportional to the amount present. For any real number x and any positive real numbers a and b such that b is not equal to 1, an exponential growth function has the form f of x equals a times b to the x. Note that this is the same as a times b to the x. It's important to note that that exponent only belongs to the base b. A is a coefficient. Now a is the initial or starting value of the function. What this means is that when x equals 0, you'll find that initial or starting value. B is the growth factor or the growth multiplier per unit x. For example, if I have f of x equals 2 times 3 to the x, it's easy to demonstrate what the initial or starting value of the function is. Because when x is 0, I'll have 2 times 3 to the 0. That's 2 times 1, which is 2. B is the growth factor or growth multiplier per unit x. To demonstrate this, let's look at a t-table. Making a t-table out of our function f of x equals 2 times 3 to the x, let's just start with 0 and go through a few of the integers. If 3 is raised to the 0 power, that's 1, and 1 times 2 is 2. If 3 is raised to the power of 1, that's 3, times 2 is 6. If 3 is raised to the power of 2, that's 9, times 2 is 18. If 3 is raised to the power of 3, that's 27, times 2 is going to be 54. Now, when we look at how this is growing, our outputs are being multiplied by 3 to get the next output. So every unit of x, we add 1 to get the next x. The output is actually being multiplied by 3 to get the next output. And this is the key characteristic of exponential growth from exponential functions. Let's graph some exponential functions. Graph, identify the y-intercept, domain, and range, and give the equation of the asymptote. Here, y equals 3 times 2 to the x. If x is negative 2, 2 to the negative 2 is going to be 1/4. 3 times 1/4 is 3/4. If x is negative 1, 2 to the negative 1 is 1/2, times 3 is 3/2. If x is 0, 2 to the 0 is 1. 3 times 1 is 3. If x is 1, 2 to the 1 is 2, times 3 is 6. If x is 2, 2 squared is 4, times 3 is 12. We can see here that we are doubling every time. Our growth factor, or our growth multiplier per unit of x, is 2. All right, let's go ahead and graph these points. I have a negative 2, 3/4, a negative 1, 3/2, 0, 3, 1, 6, and 2, 12. And here we go, trying to connect the dots as smoothly as we can. And as we go to the left, if you need to add a few more points in there to make sure, let's say that we put in a negative 8. 3 times 2 to the negative 8. That's going to be 3 times 1/2 to the 8th. That is 3 times 1/256. So we have a very small number of 3/256 over here, but we're still on the top side of that x-axis. So we see that asymptotic behavior. The y-intercept is 0, 3. A little bit of a change from last time. We have always had y-intercepts of 0, 1. That's because this is a transformation where we are stretching this exponential function vertically by a factor of 3. So that 0, 1 down here becomes a 0, 3 instead. The domain, negative infinity to infinity. Remember where the x is? It's in the exponent, and that exponent can be whatever it needs to be. The range, usually taken by looking at the graph, is going from 0 to positive infinity. and my asymptote is y equals 0. Let's try graphing this function. We have y equals negative 2 times 2 to the x minus 1 plus 3. Looks like we have a few transformations going on here. First off, this x minus 1 shows me that I am shifting my graph to the right 1 unit. This negative 2 in front shows that I am stretching it vertically by a factor of 2, but also reflecting it over the x-axis. My plus 3 is going to shift the entire graph up 3 units. And those transformations are done in that order, the order of operations, taking the exponent transformation first, multiplication transformation, and addition transformation. So when I'm putting my numbers in here, let's say that I have an x of negative 2. So this would be a negative 2 times 2 to the negative 3 plus 3, which is negative 2 over 2 cubed, which is 8, plus 3. I end up with 11 fourths. 11 fourths. If x was negative 1, I'd have negative 2 times 2 to the negative 1 minus 1 is negative 2 plus 3. This is going to be a negative 2 over 4 plus 3, which is 5 halves. Here, a negative 2 times 2 to the 0 minus 1 plus 3. So that's going to be a negative 2 over 2 plus 3, which is a negative 1 plus 3, giving me an output of 2. For 1, 1 minus 1 is 0, 2 to the 0 is 1, times negative 2 is negative 2, plus 3 is 1. For an x value of 2, 2 minus 1 is 1, 2 to the 1 is 2, 2 times negative 2 is negative 4, and negative 4 plus 3 is negative 1. Let's try a 3. 3 minus 1 is 2. 2 squared is 4. 4 times negative 2 is negative 8. Plus 3 is going to be negative 5. Let's go ahead and put these values on the graph. Negative 2, 11 fourths. Here's 4 fourths, 8 fourths, and 11 fourths. Negative 1, 5 halves. That's going to be 2 and a half. 0, 2, 1, 1, 2, negative 1, and 3, negative 5. Let's go ahead and connect the points that we have in as smooth of a graph as we can make. This is going to go down to negative infinity, and this side will get very close to that value of y equals 3. So our y-intercept here, 0, 2. The domain is negative infinity to positive infinity. The range, because this graph was reflected over the x-axis and then shifted up, both of those transformations are going to affect this. The range is going from negative infinity to 3, not including the 3. And my asymptote is y equals 3. Let's find the equation of this transformed graph. Now the equation for this graph is going to be in the form y equals a times b to the x plus d. So we start off knowing that we have some kind of vertical shift going on. We can find that just by looking here in our graph. It looks like our graph has been moved down 4 units. So let's go ahead and write that in. I know that I have y equals a times b to the x minus 4. Now let's see if we can pick out a point to put into the function. I've got a point here of maybe, let's try 0, -2. That's a good point. If x is 0, then y equals -2. Well, b to the 0 is just 1, so I have a minus 4 on the right and -2 on the left, and a is equal to 2. So now I have that part of my graph. I know that y is equal to 2 times some base, I'm not sure what the base is quite yet, to the x minus 4. Can we find another point to put in? Let's say maybe we put in the point -1, 2. So when x is -1, y is +2. And I see if I can solve this. I'm going to go ahead and add 4 to both sides. This gives me a 6 equals 2b to the -1. I divide both sides by 2. That gives me 3 equals b to the -1. Well, if I can raise both sides of this equation to the power of -1, that will give me a b. And 3 to the -1 is 1/3. And it looks like I have all the pieces I need now for my equation. The equation is y equals an a of 2 times a base of 1/3 to the x minus 4. Now let's see if we can find the exponential function f of x equals a times b to the x, whose graph goes through the points 0, 4 and 2, 16. Let's start with the form they gave us. Y equals a times b to the x. Now I have this point of 0, 4. This really simplifies things quite a bit because I can say a times b to the 0 equals 4, substituting in 0 for x and 4 for y. I know that b to the 0 is just 1, so straight away I find that a equals 4. Next step. Let's rewrite our model. It's y equals a, which we found is 4, times b to the x. I still need to find out what b is, but I have another point I can use. This will be 4 times b to the x of 2 will give me a y of 16. Let's divide both sides by 4, trying to solve for b, and then I take the square root. I know that my base is going to have to be positive, so I'm only going to take the positive square root of 4, which is +2. This means that my function is y equals 4 times 2 to the x. Remember, we can write this as f of x equals a times b to the x as well. So f of x equals 4 times 2 to the x. Let's find the exponential function whose graph passes through the points -1 5/3 and 3 135. Let's start with our standard of y equals a b to the x. Now this is a little more difficult because they have not given me a point where the x is 0. So it gets a little bit more involved here. Let's go ahead and start though with this point of -1 5/3. Y is 5/3 when x is -1. This means 5/3 equals a over b. This is going to mean for us, if I multiply both sides by b, a is equal to 5/3 b, or 5b over 3. Now I don't know what a is numerically, but I do know what a is in terms of b now. Let's see if we can try this again. Y equals a b to the x, where we replace the x with 3 and we replace the y with 135. Now, I do know that a is 5/3 b, so let's substitute. 135 is a, which is 5/3 b, and still times another b cubed. This means 135 equals 5/3 times b to the 4th. Let's multiply both sides by 3/5 so that we can isolate the b to the 4th. Now 135 divided by 5 and then multiplied by 3 gives me 81. 81 equals b to the 4th. Now if I take the 4th root of that, I know b is going to be only the positive 4th root of 81, which is 3. Now that I know what b is, I can substitute that back into this equation to get my a. This means 5/3 times my b of 3 is equal to a. This means a is 5. I have all my pieces now. Y is equal to 5 times 3 to the x.